Dear students, welcome to the unit number 4 of Software Engineering course. This unit is concerned with the system in which it resides must be understood. To accomplish this, the overall objective of the system must be determined, the role of hardware, software, people, database, procedures and other system elements must be identified, and operational requirements must be elicited, analyzed, specified, modeled, validated and managed. These activities are the foundation of system engineering. A system engineer works to understand system requirements by working with the customer, future users and other stakeholders. Objectives and more detailed operational requirements are identified by eliciting information from the customer. Requirements are analyzed to assess their clarity, completeness and consistency. A specification, often incorporating a system model, is created and then validated by both practitioners and customers. Finally, system requirements are managed to ensure that changes are properly controlled. An effective representation of the system must be produced as a consequence of system engineering. This can be a prototype, a specification or even a symbolic model, but it must communicate the operational, functional and behavioral characteristics of the system to be built and provide insight into the system architecture. The elements combine in a variety of ways to transform information. For example, a robot transforms a command file containing specific instructions into a set of control signals that cause some specific physical action. Creating an information system to control software to support the robot requires system engineering. Computer-based systems is that the elements constituting one system may also represent one macro element of a still larger system. The macro element is a computer-based system that is one part of a larger computer-based system. As an example, we consider a factory automation system that is essentially a hierarchy of systems. At the lowest level of the hierarchy, we have a numerical control machine, robots, and data entry devices. Each is a computer-based system in its own right. The elements of the numerical control machine include electronic and electromechanical hardware, for example, processor and memory, motors, sensors, software for communications, machine control, interpolation, people, the machine operator, a database, the stored NC program, documentation, and procedures. Of its domain of focus, system engineering encompasses a collection of top-down and bottom-up methods to navigate the hierarchy illustrated in the figure shown. The system engineering process usually begins with a world view. That is, the entire business or product domain is examined to ensure that the proper business or technology context can be established. The world view is refined to focus more fully on specific domain of interest. Within a specific domain, the need for targeted system elements, for example data, software, hardware, people, is analyzed. Finally, the analysis, design and construction of a targeted system element is initiated. At the top of the hierarchy, a very broad context is established, and at the bottom, detailed technical activities performed by the relevant engineering discipline, for example, hardware or software engineering, are conducted. Stated in a slightly more formal manner, the worldview is composed of a set of domains which can each be a system or system of systems in its own right. Stated in a slightly more formal manner, the worldview is composed of a set of domains which can each be a system or system of systems in its own right. Worldview is equal to D1, D2, Dj up to D. Each domain is composed of specific elements, each of which serves some role in accomplishing the objective and goals of the domain or component. Di is equal to E1, E2, E3 up to En. Finally, each element is implemented by specifying the technical components Ck to achieve the necessary function for an element. Ej is equal to C1, C2, C3 up to Ck. In the software context, a component could be a computer program, a reusable problem component, a module, a class or object, or even a programming language statement. System engineering is a modeling process. Whether the focus is on the worldview or the detailed view, the engineer creates models that define the processes that serve the needs of the view under consideration, represent the behavior of the processes and the assumptions on which the behavior is based, explicitly define both exogenous and endogenous input to the model, represent all linkages, including output, that will enable engineer to better understand the view. To construct a system model, the engineer should consider a number of restraining factors. Assumptions that reduce the number of possible permutations and variations, thus enabling a model to reflect the problem in a reasonable manner. Simplifications that enable the model to be created in a timely manner. To illustrate, consider an office products company that sells and services a broad range of copiers, faxes, and related equipment. The system engineer is modeling the needs of the service organization and is working to understand the flow of information that spawns a service order. Although a service order can be derived from many origins, the engineer categorizes only two sources: internal demand and external request. This enables a simplified partitioning of input that is required to generate the service order. Limitations that help to bound the system. Constraints that will guide the manner in which the model is created and the approach taken when the model is implemented. Preferences that indicate the preferred architecture for all data, functions, and technology. The resultant system models serve as alternative solutions to the problem at hand. In essence, the system engineer simply modifies the relative influence of different system elements, people, hardware, software, to derive models of each type. System simulation is the use of a computer to represent the dynamic responses of one system by the behavior of another system modeled after it. A simulation uses a mathematical description or model of a real system in the form of a computer program. This model is composed of equations that duplicate the functional relationships within the real system. When the program is run, the resulting mathematical model forms a similar behavior of the real system with the results presented in the form of data. A simulation can also take the form of a computer graphics image that represents dynamic processes in an animated sequence. System simulations are used to study the dynamic behavior of objects or systems in response to conditions that cannot be easily or safely applied in real life. For example, a nuclear blast can be described by a mathematical model that incorporates such variables as heat, velocity, and radioactive emissions. Additional mathematical formulae can then be used to adjust the model to changes in certain variables, such as the amount of fissionable material that produced the blast. Simulations are especially useful in enabling observers to measure and predict how the functioning of an entire system may be affected by altering individual components within that system. In engineering, computer models of newly designed structures undergo simulated tests to determine their responses to stress and other physical variables. The goal of business process engineering is to define architectures that will enable a business to use information effectively. Nowadays, business processes are changing rapidly. The price for this change is largely borne by the IT organizations that must support this polyglot configuration. Today, each IT organization must become, in effect, its own systems integrator and architect. It must design, implement, and support its own unique configuration of heterogeneous computing resources, distributed logically and geographically throughout the enterprise and connected by an appropriate enterprise-wide networking scheme. Moreover, this configuration can be expected to change continuously but unevenly across the enterprise due to changes in business requirements and in computing technology. These diverse and incremental changes must be coordinated across a distributed environment consisting of hardware and software supplied by dozens, if not hundreds, of vendors. The technology infrastructures. The infrastructure encompasses the hardware and software that are used to support the application and data. This includes computers, operating systems, networks, telecommunication links, storage technologies, and the architecture that has been designed to implement these technologies. Lectures described earlier, a hierarchy of business process engineering activities is defined. Referring to figures shown, the worldview is achieved through information strategy planning. ISP views the entire business as an entity and isolates the domains of the business, for example, engineering, manufacturing, marketing, finance, sales, that are important to the overall enterprise. ISP defines the data objects that are visible at the enterprise level, their relationships, and how they flow between the business domains. The domain view is addressed with a business process engineering activity called business area analysis. Here describes business area requirement engineering. The outcome of the system engineering process is the specification of a computer-based system or product at the different levels described generically in figures shown. Requirements engineering provides the appropriate mechanism for understanding what the customer wants, analyzing need, assessing feasibility, negotiating a reasonable solution, specifying the solution unambiguously, validating the specification, and managing the requirements as they are transformed into an operational system. The requirements engineering process can be described in 5 distinct steps. Requirements elicitation, requirements analysis and negotiation, requirements specification, system modeling, requirements validation, requirements management. Requirements engineering process can be described in these steps. Problems that help us understand why requirements elicitation is difficult are described below. Problems of scope, the boundary of the system is ill-defined, or the customer's users specify unnecessary technical detail they may confuse rather than clarify overall system objectives. Problems of understanding. The customer's users are completely sure of what is needed, have a poor understanding of the capabilities and limitations of their computing environment, don't have a full understanding of the problem domain, have trouble communicating needs to the system engineer, omit information that is believed to be obvious, specify requirements that conflict with the needs of other customers' users, or specify requirements that are ambiguous or untestable. Problems of volatility. The requirements change over time. To help overcome these problems, system engineers must approach the requirements gathering activity in an organized manner.